So, I'm David Redden. I am the ex-chair of Biostats, thank God. I had served in that role for 4 years, but I stepped down as vice chair, and I'm also full professor in the School of Public Health. I am also the director of the Center for Clinical and Translational Sciences BIRD unit. Oh, I can have so much fun with that acronym. But it's the Biostatistics, Epidemiology, and Research Design group. We call the leaders the big birds, the little birds, and we got to deal with the little birds, and then we deal with the bird crap and things like that. But that's usually not what I'm saying. So I'm going to give you an overview of biostatistics. First, how many of you have had a statistics course? How many of you found that abysmally painful? Thank you for your honesty. How many of you have not had a stats course? Wait a minute, I'm missing here. I mean, how many of you can't remember if you had a biostats course or a stats course? All right, here's this approach, okay? This lecture has something for everybody, and the first thing I say in graduate school, and this is offensive to people entering graduate school, is, well, just forget everything you think you know, because I'm going to tell you they taught you wrong, and we're starting over. Because what we do typically is the typical introduction is almost as if it's algebra. And if you go at it with the formulas, then you learn the mechanics, but fail to understand the most important question, which is always, why would I ever do this? Why does this matter to us? What benefit is there to this science? So this discussion is going to go directly there. By all means, I didn't make handouts. We want to email them the slides later today. You do not have to take notes. You are free to contact me at any time that you may need help. I am available to everyone through my appointment with the CCTS, and there are 2 clinics that run weekly, one on Monday from 10 to 2 in the Edge of Chaos. The other one runs 11:30 to 1 here in this room on Wednesdays. That one has lunch, so you might have free lunch at that. So you might want to attend that one, but if you want me, you need me on Monday, just come by. We'll sit down and talk about any problem you got and any design. And my advice to you is do your best to always throw a ton of quotes in here from the founders of statistics and all the other quotes, because I just like quotes. Never think that you just need a statistician or a methodologist at the point of it's time to analyze the data. No. R.A. Fisher, who is the gentleman who developed the majority of our statistical theory, near the end of his life made a comment at a conference that is quoted quite often. To bring a data set or an experiment to a statistician after it is completed is to request a post-mortem examination. We will tell you exactly what your experiment has died from. So it's important, and it's one of the things I really struggle with, that I really work with, is to be there day one. Let's make this a collaboration. If you're going to be a translational scientist, I do firmly believe you have to understand team science. Team science means that it's a team of skills coming together. I firmly believe in collaboration. The definition of collaboration is when you get a group of people together that contribute their skills to a problem to achieve an outcome that exceeds what anyone alone could do. I'm not going to try to turn you into PhD biostatisticians today. I'll be honest, I'm not certain I should have been turned into one. But I want you to understand the fundamentals, and after today, be able to have a conversation about it. And after today, be so confident in the correct approach to it that you know that you can come in and talk to anybody, and you can interpret anything in the literature that is using inferential statistics. That's the goal for today. How long do I have, Eve?
9 maybe.
Huh? Oh, good. Including a break. Including a coffee break. That's great. Okay. So, always, I'm going to give you a brief overview of statistics and what is inference. And I'm going to tell you every stinking book out one of these days, I'm going to write a book. Promise you, I'm going to write a book before my career is over, because every stats book out there does it wrong. I'll start with, here's the formulas, and you get confused. You're just berated with these formulas. Okay, well, my textbook, I'm going to put probability first. I'm going to save those formulas until at least chapter 3 or chapter 4. Because that's where things go wrong. Then we're going to have our basic probability distributions, okay? So that you understand some teaching examples of where these distributions, you know, we look at all these crazy distributions in my textbook. At every distribution, I'm going to give you this type of outcome follows this distribution. We would expect this outcome to follow this. These are the, and I'm going to give you some of those examples. Then I need you to understand something. The reason we care about probability is statistics follow probability. They have to. Okay, and I'll tell you why they have to. Give you the classic teaching example of, here's a statistic that follows a distribution. That's why we beat the central limit theorem to death. I'm going to take the time to give you key terms correctly defined. Okay? You don't have to memorize these. If you try to memorize them, I'm going to be offended personally. I'm going to give you an example that will ground every one of these terms into their correct meaning, that you won't get lost. We'll play true-false, and then I'm going to give you the truth about statistics. If you're confused by statistics, there's a good, valid reason. We had two warring camps that hated each other, that came with two separate approaches and two separate theories. What did we do in the late 80s and the early 90s? Smashed it together and blended right over it in every textbook. Guess what? That leads to a lot of confusion, because it seems like the terms don't align. You know why? Because they don't align. Talk to you about some examples. If I've got time, I'll get you to power. You're going to laugh at me. I can't walk down that street without somebody stopping me and saying, can you do a power calculation for me? If somebody pulls me over, I'm not certain if they're asking me for directions or they're going to ask me, can they meet with me for a power calculation? Okay? And then I maybe not get there. Maybe if we have some time, or maybe later in the year, we can all get back together and get through correlation and regression. All right? So, open up any textbook. This is the way it goes. Any introductory stats book. Summarizing data, descriptive statistics, then the laws of probability, then the probability distributions, which is binomial, Poisson, normal, all of these things, and it goes hypothesis testing. And to me, when I teach every introductory course, I tell the students day one, you're going to have 3 pieces. Descriptive statistics, then probability. Then I've got to teach you how those two things marry together such that they get us to a position where we can do inferential statistics. If you can't understand, if you don't really understand what a probability is, it's very dangerous to do inferential statistics. Okay? And that's what we always, if you see a p-value, you have to stop and say, what inference are they trying to make? Always remember, if you see a p-value, the first question you should ask yourself is, what's the hypothesis test? Okay, it's dangerous to put down a p-value if you don't know what the hypothesis test is. In fact, you're kind of misleading yourself. So, it's descriptive statistic, probability, statistical inference. Inference, I mean what several authors call null hypothesis significance testing. The idea of setting up an experiment. I'm going to assume this is true. I'm going to collect data. I'm collecting data to see if the evidence leads me to the alternative. I never actually collect data to try to see if it will conclude the null. That is a fact. That's a bad argument. And I will tell you why statistically. Okay? And then you go through and you get your test statistic, you get your p-value, and then you draw a conclusion. this is under great attack right now in science. And arguably, there is justification for it to be under attack. It is a common it's 4 steps. Most people can follow the 4 steps. But the catch is, when you're a hammer, that does not mean everything is a nail. And it has been used in situations which are completely inappropriate. And it has also been shown that it cannot handle certain current scientific problems. Metabolomics is kicking its butt. Genetic studies kicking its butt. So we've got the technology has run further, and science has run further than this has evolved. That just means we've got to come up with new appropriate methods. So be mindful, not everything has to have a p-value. Nor is a p-value always appropriate. When I teach, I prefer, and when I will write my textbook, I'm going to start with probability distributions, then get you to statistics, then get you to statistical inference. Because to me, you should always first start with that concept of what's a probability? Why? Why am I so adamant about this? Because I took 6 years of graduate training to have this burned into my skull. Everything that is valid data, and notice I was very careful with that. I'm not certain everything that is recorded is data, okay? But everything that data sets, or data such as, and when I think of data, and maybe I should change it. I'm going to change my slide to observations. I think that's a better term. I want to take data out of there, because I think that word has become confusing. If I was going to collect observations, I believe those observations follow a distribution. That there is a probability distribution behind it, governing what I can observe. Okay? That probability distribution is actually hidden from my eyes. I cannot directly get to it. Therefore, I have to collect data, or I have to get observations that are being spit out from that probability distribution. And then if I summarize that data, then I am going to start deducing or inferring, like Sherlock Holmes, what is it that's hidden from my sight? Because there's a classic truth. There is a truth. Okay? Truth. The data cannot deviate very far, or the observations cannot deviate very far from the probability distribution generating it. Okay? If I brought my 3 daughters into this room, if I threw a picture up there, all of you would go, holy crap, I know who the father is. Because they all have a lot of my characteristics. My wife jokes about it. They all have my chin. You can't see it. They all have my eyes. Because I am the parent, the child inherited my characteristics. All observations are a child of a probability distribution. Period. I will not deviate from that statement. All observations are a child of a probability distribution. The only question I have to ask, where is that probability distribution centered? How much spread is in that probability distribution? Are there 2 distributions in the data set, in the set of observations? Should I believe there's 1 probability distribution lurking in here? Should I believe there are 2? Possibly there could be 3. How do I go about making those judgments? That's what this is about. But you must think, because here's the thing. When I get anything, any data set, any set of observations, my training is first to stop. I don't even start calculating anything. I look at it and I think to myself, what probability distribution could have possibly generated these observations? Okay? Because I need to understand that. Understanding that helps me know where the next step should go. Okay, so it's always the probability distribution passes its characteristics into the observations. From the observations, I can calculate descriptive statistics. Okay? And from those statistics, I can make judgments about probability distributions. Okay? Then that's the goal. Now, let's get this a little concrete. Suppose I choose to randomize in an experiment, in a controlled clinical trial. I randomize people to drug A and to drug B. And I am looking at survival times. So I do this. I run a 5-year study. And I start studying my observations. I'm hoping that drug B leads to a greater survival compared to drug A. What does that imply to a statistician? That implies there are 2 probability distributions. I need to go in and see if there's only one probability distribution that is controlling survival, then there's no difference between drugs. If there are 2 probability distributions hiding in the data set, and they are in the correct sequence that I have hoped, then I've got evidence that drug B is superior to drug A. So that's the idea. From the observations, I am trying to deduce characteristics of the probability distribution and know what, because if the drugs are effective, they should create separate probability distributions. Okay, so let's get some examples. Nature. I love nature. So, weather gives us plenty of data and plenty of observations, such as the number of hurricanes per year. Anytime you hear a statistician say per year, per, said by a statistician, implies a distribution such as the Poisson. Okay? Just a trick to help you understand that if you're talking about those types of things, per implies you're counting them and you're giving a specific time window. Statisticians are trained to think, okay, that data, I'm going to see if the Poisson fits. May not. Usually the Poisson doesn't fit. But we have other things that we can tinker with. Annual rainfall, the number of tornadoes in a given month. That would be an over-dispersed, a zero inflated Poisson. Biology. This is always great. Body temperature. Now let's talk about this for a second, okay? I want to help you understand something. What is a human body temperature? Give it to me in Fahrenheit. Help me. Speak up. And I'm not that intimidating. Come on. 98.6 Fahrenheit. You walked in my trap, sorry. That's the average body temperature. Do you really think every one of us in this room is sitting right here, right now at 98.6? Absolutely not. Okay? We're not. That's the average body temperature. That's the center. It's where we believe the center of the probability distribution is. People naturally vary around it. If there's variation or expected variation, then you're in the world of probability. Okay, at that point, when you know it varies from person to person, you have now entered the world of probability. And that's where we have to bring in statistics to mix it. And I'll give you a very concrete example. Okay, that's the average. I don't know why. I can't tell you why. But I knew my mom passed away 28 years ago when I was 21, and so the siblings, because Dad aged, me and my siblings were watching over Dad. Dad also passed away about 5 years ago. But he had a really long life, really great life, But his kidneys started to fail late, mainly because he'd been obese all his life. My dad, not trying to be disrespectful, my dad led off the obesity epidemic. He set the trend. He was always a huge guy. But the kidneys were out. Heart didn't wear out, so kidneys did. He started getting serial kidney infections. It was one there. I can remember being in the hospital with him, sitting by the bed and just chatting with him. And the nurse comes in and I said, excuse me, what is his temperature? Well, your dad's fine. He's 98.2. I looked at her and I said, I think you probably should culture him. She looked at me like I had lost my freaking mind. I said it was 98.2. I said, I know. But I've never been with my dad, been around him long enough to know that my dad does not run at 98.6. Dad is always, for all his adult life that I've known him, running around 97.5. Dad rarely had a body temperature above 98. Don't ask me why. Somehow his thermostat was set wrong. I don't know why. She looked at me and said, I don't believe it. 2 days later, and he's got another kidney infection. So it's a matter of knowing, by studying or watching Dad's body temperature over time, we all recognize Dad's not running at normal temperature. So we've got to be prepared that it just elevates anywhere close to something maybe wrong. Blood pressure, one of my favorite ones. Body weight. Body weight typically follows a normal distribution, the bell. Engineering, some of my favorites. M&Ms. M&Ms are my favorite because I teach probability to the undergraduates using M&Ms. That's a multinomial distribution. Things going on in healthcare, such as things like I said, survival, that follows a specific probability distribution. I'm not trying to get you to know all of these. I want you to know that you need to get to somebody who can help you and have the language of, hey, when I go and design this study, when I'm going to collect these observations, what do you think the likely distribution is going to be? And start that conversation there, and just go back and forth. So variation underpins the concept of probability distribution. Probability distribution is the hidden mathematical characteristic, and it gives me the tendencies, where the center is, and the variation. Have you ever wondered something? You go to a medical journal and you look. Table 1, what's there? Sample means and standard deviations. Why? Typically, you only need those two characteristics to really get a good idea. There are three characteristics I study as a statistician. Where the center is, that's the sample. That's what the mean is. How much variability is there? And typically, I worry about the shape. I'd like to know what the shape of it is, because the shape helps me know which of the statistics is most appropriate. Okay? It also tells me where I might get my rear end into trouble when I start calculating probabilities. But that's why in table 1 you'll always see the mean, or the average, and the standard deviation. Okay? Because those two things are essential to understand the most fundamental concepts of probability. Where's the center? How much is it spreading out? Because if I gave you a standard, if we got two groups and the mean survival in this one is 6 months, and the mean survival in the next one is 5.9 months, do you really think there's a difference? No, probably not. Okay? So that's why we use those. All right, some more. Why are we not advancing? Oh, there we go. Just was not going fast enough. So the normal distribution, continuous distribution, continuous ideas, such as height. Height typically follows a normal distribution. IQ is designed to follow a normal distribution. We know the probability distribution governing IQ is centered at 100. We know it has a standard deviation of 10, which means that it guarantees certain properties that allow us to know what's going on. Okay? Typically, if you're 3 standard deviations below or 2.5 standard deviations below, my wife being a psychologist reminds me that's where we typically indicate that there is a learning disability or a significant disability. Okay? Poisson, always love Poisson. They're always my favorite. I don't love teaching it, but it's always anything that's measured in space or time. How many texts will you get in the next hour? Space and time. The number of texts in the next hour. You've got a given window, It's a count. Some of my favorite ones that I teach with are when I try to impress the undergraduates, the number of unexploded bombs per square block Tokyo. That follows the Poisson distribution because there are still American bombs buried in the blocks of Tokyo. They find them every now and then. It's not a huge number, but they're out there. If you're a cooking buff, the number of truffles per acre follows the Poisson. The other one that's always fun, because I always enjoyed like studying shipwrecks and things like that, the number of shipwrecks per square mile on the bottom of the Atlantic follows Poisson distribution. Okay? Binomial distribution, the number of successes and failures. Binomials are very common. It's one of the most common used distributions that we make inferences on. It's just yes or no. It's yes or no. Male, female, you've got two categories, that's what you've got. It's nominal. It's not even a number. It's a characteristic. Okay? And then the multinomial distributions, M&Ms, well, like I said, one of my favorite teaching examples. And then genotypes and haplotypes, because we've gotten so much into the genome, they follow a multinomial distribution. We don't, I dare you to go find a journal that you get to see the observed data. We never put that data into the actual paper. We put the statistics in. You'll always find the two. You'll find the sample mean, which is nothing more than, hey, when you're in college, when you were in high school, how did you know what your grade was? It was your average. Sum up all your tests, divide by the total number of tests. That's what the teacher was going to assign you as your grade. And that's the fundamental calculation of statistics too. Sum up all the data, divide it. That gives me some idea of where the center of the observations are. Here's the cool fact. The center of the observations is the best predictor of the center of the probability distribution. Why? Because the probability distribution must pass its characteristics into the observations. What characteristics is it passing? The center and the spread and the shape. They will not be. So if I can calculate from the observations a sample statistic, I can use that as my best estimate of where the center of the probability distribution is. Same thing, I need to have some sense of spread. How much is it spreading out? And this is kind of odd. Why do the statisticians have to make this so complicated? All right, just ignore this. This is technically the average squared deviation. How far is each data point falling away from the center? I'm squaring it, and then I'm dividing by n minus 1. Two things. Why the heck did you square it? Because if I don't square it, it sums to 0. By default, mathematical principles say it has to sum to 0. Why didn't you take the absolute value? Because squaring things is a lot easier in the 1700s and 1600s than taking the absolute value. And third reason is because if I square it, I know I force it to a specific distribution. Okay? Why n minus 1? Because I had to use the sample mean, which was calculated from the data. Every time I use a statistic in a calculation, I give up 1 degree of freedom. You hear this magic word used by statisticians, degrees of freedom. It's actually the number of unconstrained data points that can be used in a calculation. The number of unconstrained. Because I already told you, I know for a fact, if I sum that quantity right there, it goes to 0. If I don't square it, if I lose the square, that's got to be 0. That's a constraint right there. So I have to give up a degree of freedom. All right? All right, cool facts. Because the data inherits characteristics from the probability distribution, I can use statistics to be Sherlock Holmes. And I can do these games of taking all this data and starting to make judgments and solving the great mystery that's out there. I can infer the characteristics. I like the word infer because it's really what I'm doing. Under certain assumptions, you know the probability distribution that governs the descriptive statistic. See, that's the big step. When I'm in the undergraduate honors class, I actually make them not explain, they don't get to recite the central limit theorem to me. They have to explain to me why it's important. That's the question that's put down. Why is the central limit important? Because it's the first hint that the statistics, I told you that observations follow probability distributions. I told you the number of tornadoes, the number of hurricanes, the number of shipwrecks. I told you height, IQ, they follow distributions. But the central limit theorem tells you statistics also. Everything I calculate also can be mapped to a probability distribution. Why do I care? Because I told you that too. 3 standard deviations below an IQ test is a warning sign. Something's not right. By studying what is extreme, I can make judgments as to this is typical or this is atypical. And I can do the same thing for statistics. If I believe the probability distribution is centered at 10, better yet. Basic quality control example. Huge fan of beer. Huge fan of beer. Makes me a jolly good fellow. Right? Give a reference. No Tom T. Hall fans in the room. There's a song called that. By Tom T. Hall. Beer bottles, 12 ounces. Okay? 12 ounces. I go and I select my favorite beer, Fat Tire, and I go, hold on, those little bottles, and they're all 6 ounces for $1. Besides, I got judged. Something went wrong with the filling machine. Because there's no way that anything that should average 12 is all of a sudden averaging 6. Right? So by understanding that the probability that the sample mean fell so far away from the expectation of 12, we can make a judgment. Something's changed in that probability distribution. Something changed with the mechanism. The mind-blowing fact is the probability distribution of the description may differ from the probability distribution that generated the observations. That's the mind-blowing fact. Is just because I got a binomial distribution governing your data, your test statistic may actually follow a normal distribution. That's why you kind of collaborate with statisticians to know, am I constrained here? How can I move from this distribution to this distribution? And which one is most beneficial? Which one will give me the most power? Okay? So again, when I went to graduate school, they told you to emphasize, if you're going to give a lecture, at best, depending on the length of your lecture, if it's a short lecture, one key fact and hammer it over and over. Longer lecture, you can get 2 facts in. An hour and a half, maybe you can get 3 key facts in. Here's your first of your 3 key facts. I want you to remember this. Okay, you can forget everything else I rambled about. This is one of your 3 to keep in mind. You're going to go out and do science. You're going to collect observations. You're starting here. Here. You're going to go down here. But the real meat of the matter is hidden to you. The real thing you're trying to get to is the data's great, only in the sense that it helps us understand what's lurking behind the groups, the treatments, the interventions. If interventions work, I generate 2 probability distributions, not 1. Okay? If I give 3 drugs and 3 drugs are having different outcomes or leading to different outcomes, I will get 3 probability distributions. Those drugs have no impact whatsoever. So that's the catch. I design an experiment, collect my observations, make my inference, but in the background, I'm really making judgments about probability distributions. Okay? So that's one of your key three. Now you're teed up to know that there's going to be two more. Okay? Sometimes I've thought about taking this completely out. Okay? But there's a key point here. Okay? I also tortured the undergraduates by, after saying why is it important, then I tell them to write it out for me, and they get it wrong all the time. They get it wrong all the time. You know, I lecture about it. Why do we give a darn, trying to improve my language, don't worry about the central limit theorem? I'm sure y'all have all seen this, but nobody ever answered the question, why does it even matter? I'll tell you why it matters. The sample mean will follow a normal distribution. A sample statistic has now been linked to probability. I can take a statistic and judge, does it match a probability distribution, yes or no? That's a key thing that helps me make judgments. Okay, that's why I put this here. I know by mathematical principles, and I had to take 6 years to be certified that I could do it right. I can take observations, and I know I can get to certain statistics, and then I can get them to a certain probability distribution. And from there, decide, have I seen what we would expect, or are we observing something that is so extreme that, I have to conclude my assumption about the underlying probability distribution is wrong. That's the whole game. The only reason I put this here, not to impress you with my ability to find Greek letters in Word, but simply to say a statistic, probability distributions pass their characteristics into observations. I can take those observations and create statistics, and I can take those statistics and link them back to probability distributions. That's what I do for a living. Okay, so here's my fun. All right, this is where we get really interactive. Okay, which means I start reading more. All right. God, we go through so much damn gum chart and statistics and stuff. Okay, so let's me just stop trying to read over my shoulder. I'm trying to walk through. I'm not that wide though. So listen to who wants to talk to me? Who wants to talk to me? Who wants to teach statistics right now? The first rule of rule is not to look down, because at that point when you break eye contact, you're it. You're it. You broke eye contact. Sorry. All right? So talking about this. In a jury trial. What is assumed?
Innocent children.
No, you went too far. You just stopped at innocent. You went over something. Right? So there is a belief. We come in. There is something that is assumed to be true. There is a null hypothesis. There is something that is assumed to be true. We will hold it as fact. It is the person is innocent. What is the other hypothesis in a jury trial?
The person is not innocent.
The person is guilty. I will take not innocent, but we use the phrase guilty. Those are mutually exclusive. You cannot be in both of them at the same time. And they are opposites of each other. They are exclusive and exhaustive. Those are the only two possible outcomes. Either you are innocent or you are guilty. Thank you. Would you like to pass the game to a colleague? You've survived.
Zach looks excited.
Zach looks very excited. Congratulations, Zach. So we have defined the null hypothesis. When I do an experiment in medical literature and I am relying on probability distributions, I will assume that we will put an equal sign in the null to say, I believe the probability distribution is centered here. I will create an alternative that is mutually exclusive and is the opposite. So if I've said equal, the alternative must be not equal. Never forget that. You know what a null hypothesis is. It is what is assumed to be true at the beginning of the trial. Older stats textbooks actually don't call them statistical experiments. They don't even call them statistical inference. Older textbooks actually use the phrase statistical trial because it's a one-to-one correspondence. Okay, so let me ask you something, Zach. Zach, you look so thrilled.
Excited.
Huh?
Super excited.
Great, glad to hear it. Have you got enough coffee?
Not quite.
Okay. 5 more minutes, we'll get more coffee. When prosecution comes in, why do we bring a grand jury together? Why do we bring a jury together? Are we looking for, when the evidence is presented, it is evidence of what?
Of guilt.
Of guilt. Never forget this. The evidence is not collected to demonstrate innocence. That's already assumed. All evidence that will be presented by prosecution is designed to see if it provides sufficient, convincing evidence that the null is not true. Okay? To ground this even further, suppose that you find out on Monday morning that your favorite stats professor has now been incarcerated because somebody died down at Uptown tonight, and that I am the prime suspect. And we go to trial, and the evidence is presented that my cell phone was traced there, okay, and that I was in the area at the time of the murder. Sufficient? Sufficient? Okay. Why? Because, hey, you might find out that it's my anniversary. I was there with my wife, and I had a dinner reservation. However, if prosecution comes in and says, well, we found the knife, and the blood of the victim, the DNA matches the blood, his DNA is on the knife, his fingerprints are on the knife, we found the gun, the ballistics match the gun, his fingerprints are on the gun, we found the rope, all this thing. If you get all that preponderance of evidence, it does not agree with what belief? It does not agree with what?
Essence of the null.
Right. It does not agree with the null hypothesis. That's what you're asking. Is this incompatible with the null? Is always the judgment. Is it incompatible? Now, as a statistician, that's the p-value. The p-value is always that magical, mystical number. It's always the summary of all my evidence distilled into one number. And it is a probability. By the way, what are probabilities trapped on? Probabilities must be between 0 and... I went and interviewed for a job one time, and I was looking at the posters of the Department of the School of Public Health, and I looked up and I saw p-value of 1.5. I thought, not certain I want to join this. But understand this. This is a key thing. The p-value is the probability of observing the data or data that is more extreme given the null hypothesis is true. Remember, the jury must evaluate the evidence under what belief? Under what belief must they evaluate the evidence? What's assumed?
Yes.
Innocent. I have to evaluate all of my evidence under the belief that what I have stated in the null is true. Okay. How do we move from, hey, Zach, who do you want to pass it to? You're off now.
Zach.
Hey, Zach, number 2. Zach, how do we move? What is the magical phrase in our literature or in our society that allows us to move from the belief of innocent to guilty. Evidence beyond what? Oh, you don't watch enough TV. Anybody can help out here? Evidence?
Reasonable
doubt. Thank you! Perfect. Exact number one. Evidence beyond a reasonable doubt. Not a shadow of a reasonable doubt. That is a misnomer. That is actually introduced by Perry Mason in a TV show. There is no shadow. It is evidence beyond a reasonable doubt. And a reasonable doubt is defined mathematically for statisticians by a type 1 error. The probability of rejecting the null hypothesis given it is true. Okay? Typically, we allow alpha to be about 5% or 0.05. All probabilities are trapped between 0 and 1, but if I see something that is beyond or below, so rare that it should have occurred less than 5% of the time, I go from innocent to guilty. That's it. And a lot of debate about should it be 0.05, should it be 0.01, should it be 0.0001. That's a debate that's been going on forever. But always remember, anytime you conduct a trial, you can make two errors. Two errors. Now remember, a type 1 is I reject the null when it is true. So in a jury trial, what's a type 1? I reject the person is and declare they're guilty and I put them in prison. Type 1 error in a jury trial is I have convicted an innocent person. Now arguably we want that to be very low in our society. Okay, so we put that's why we want beyond a reasonable doubt. We do, our system was designed to try to stop and to make that as low as possible. You cannot make it 0. You cannot do a trial and make it 0. You make it 0, and I'll guarantee you this, you will consistently make the only other error possible. What's the second error that can be made in a trial? You fail to reject the null when it is false. That's called type 2. What's that equivalent to in a jury trial? A guilty man goes free. And because the way our system was set up, generally we would allow that to happen far more often than the type 1. Now, you can debate today, does the system still work? We can have that debate over beer if you like. I'm available after 4:30. Power, the probability of rejecting the null hypothesis when the null hypothesis is false. That's what you want to do. You want powerful experiments. You want to be able to design experiments that if the alternative is true, drug B is better than drug A, you want to be able to bring convincing evidence of that and get it done. We'll get to correlation in a little bit, but a correlation, one thing I want you to emphasize here, be careful. Correlation is a wonderful tool, but it only measures linear. It's looking and studying lines. So if you hear someone say there's no correlation, oh, then there's no association. Wrong. You can't say that. You can say there's no linear association. There could still be a relationship. I just can't model it in lines. All right? Okay, I have rambled successfully. I'm going to give you 5 minutes. I'll give you 7. Go ahead. And then because I got to kick it up a notch to get through this, okay? And then remember, when you come back in the room, the first question is, what's the p-value? I got Zach 1, Zach 2.
We do a round introduction.
I'll keep it going.
I can't imagine.
Well, I'll just let Zach do it.
Keep passing those on.
Keep moving it on.
So what's the probability that when they leave here, they'll be mad at each other for passing those?
They don't get mad at each other, but it just keeps them engaged. Actually, the graduate students and the undergraduates actually love the fact that I will say, I'm going to call on you, but if you're not certain, you're allowed to cut it. And they will do it. It keeps them engaged.
Yeah.
Any questions? Y'all are not addicted to coffee, are you? Or the sweet stuff. Well, never mind, thanks. This is my son.
It's hard to reject what's hard to free it all. How's your knee?
Still association.
She's just like
That's your sugar today?
pretty good. Just starting to reach out probably. Just hearing
But there's still association.
Sure. Harvey's. Presenting methods, things like that. Students here. Very, very diverse groups. They're all pretty open. I'm not going to reach out and talk about there's a guy who
The new job is full time.
they have research saying I'm just putting pretty like
What can we salary, right?
Yeah.
Oh, she's very nice. How did you find out the job? I emailed them yesterday. And I think they're, they have it back, and it's ready to people that,
Hey, you just gotta be on top.
so we can work together though, or
Take
on
forever
the
to
same
get
division.
here. Yes.
So you should come to our next quarterly division meeting.
I'm sitting here like, granted though, yeah, mine's like doesn't really matter. I can't do anything until I meet with Dr. Jones. So it'll be fine. I just gotta make sure I have everything else ready. I can go to writing back. I have to submit an entry.
Next,
No data, like my
is
background.
next Tuesday, July 3rd, 7 a.m. to 8 a.m.
So like, so the graduates like that, everyone.
Yeah.
It's all the streets.
Comfort. Yeah.
My calculation is an average.
My wife decided to do better. And also she wants to go.
Yeah, you're like, oh, you're great.
So they're being asked these questions after. Yes. Good. Are you want to use it faster? Yes. Tell me how to say it. But it's mostly
Okay, let's go. Because I really do want to at least get through the true false thing. Because I've given you a lot of information. Boy, y'all got quiet. Wait, stack 2, who's up next? Hey. All right. So you understand that we've got the 4 steps. Okay, now he just threw you right under the bus. You're going to really come to try to read my mind. All right, but here's the thing. This is the thing about a significance test. Next lecture I would call it a try. So we always teach this. This is the second half of the stats course where you start doing the Z-test, the T-test, the 2-sample T-test, the ANOVAs, all these things, but they're all the same. They all follow the 4 same steps. So we state a null. The null in a jury trial is?
Innocent.
Thank you. The alternative in a jury trial is?
Rejecting the null.
That's step 1. They come in and they get if you watch a jury trial, that is laid out. All evidence will be evaluated under the assumption of innocence. Then the prosecution starts, and what they're doing is they're presenting their data. They're presenting their evidence. Well, that's pretty much the observations I collect in any experiment. Those are my observations, but I have to be able to distill it down to a decision time. So, the scientific method, state the, you learned it in 7th grade. I'm still doing exactly what I learned in 7th grade. I state the null and alternative. I collect the data, or the observations. I calculate a p-value and compare it to a type 1 error rate. Prior to the experiment, and we'll clarify this, because this is exactly the point where the comparison breaks down. But here's a key thing, okay? Read this sentence to me, then we'll read it back to you. Just read this piece to me. Read it to me.
No, okay.
Yeah.
The p-value is less than or equal to type 1 error rate, reject, how, what is it?
The null.
The null, yeah.
Okay. And include the alternative.
Include the alternative, yeah. It's been a while.
Would you like me to read it to you?
Yes.
If evidence beyond reasonable doubt, reject innocent and conclude guilty. I want you, the second point, I want you to never forget, okay? You saw that first chart. The other piece I want you not to forget. You get this crazy thing, p-value less than or equal to type 1 error. That is a statistician's mathematical equation for evidence beyond reasonable doubt. Because evidence to me is rare small probabilities. Things that should not have occurred if the null hypothesis is true. So anytime I put this on the board, and in fact, when I ask the students in the undergraduate program and the introductory graduate class, explain p-value less than or equal to alpha, if they put down evidence beyond reasonable doubt, I give them full credit. Because they've got it. All that is, this is nothing more than evidence beyond reasonable doubt. Okay, that's it. If I see something, if my data has a probability that is very low, that means it does not match what I expected under the null. That's it. And then I have to write a conclusion. Now here's a key thing that I have to wrestle with researchers all the time. You want one more, or you want to pass?
Oh, I'll pass.
All right, who you passing? We're all friends. It's okay for you to talk with your mouth full. Okay? So, here's the question. At the end of the trial, the jury comes back, the foreperson hands the slip of paper to the bailiff walks it to the judge is the second person in the room to know. Passes it back to the bailiff walks it back to the foreperson, that person stands and says, we the jury find the defendant. There's only two possible statements. What are they? Let's say they're going to prison.
Guilty, not guilty?
Exactly. Very good. Notice what they say. Guilty, they have concluded the alternative. But they will never say innocent. Why? They have to say not guilty.
They're assuming more evidence somewhere they don't have.
No. You cannot declare an assumption to have been found. You work the whole thing assuming the person was innocent. You can't say, now we declare them innocent, because that was a working assumption of the trial. So when you fail to reject the null, you can't say, I prove that this is true. All you can say is, I do not have evidence to reject that statement. You cannot overstate the null. Be very careful. If you get a non-significant result, all you can say is, we did not find evidence to reject that statement. Okay, be very careful with that. All right, so now the history piece, because I find the history piece very important, and I've got 20 minutes. So where did all this come from? Because it's very much in debate. You go to the literature, and it's interesting, because like I told you, this guy by the name of R.A. Fisher, he was a geneticist, but he was unsatisfied with the way he was doing his genetics research, and he decided to start doing some mathematics to kind of support some of his work, and all of a sudden becomes a great statistician, and he came up with most of our methods. But here's what he proposed, and this is what he proposed in literature. He said, state your null hypothesis. So state a null hypothesis. Provide a p-value. Calculate the p-value, report it, walk away. He didn't even give you conclusions. He just gave you the p-value. He didn't even give you... Now, think about that, okay? He's really trying to make it match to a jury trial, okay? He's really trying to make it match to a jury trial, because here's the thing that's unique about a jury trial that we don't do statistically. And by the way, those 4 hypotheses, you will not find them in literature. You won't find that written consistently that way. Well, you won't find those 4 steps in any textbook prior to the mid-1980s. You'll find hypothesis testing, but you'll find it in a different flavor. You usually have 12 people on a jury. Is there one definition of beyond reasonable doubt? Or do they have to argue it out? When they go into deliberation, why do they stay in deliberation sometimes for 2 weeks, 3 weeks? Why is it taking so long? What's going on? They don't have a common definition of beyond reasonable doubt. Everybody has to set their own, and then they have to all come to an agreement. And they argue it back and forth. That's what Fisher was trying to do. He was trying to put the p-value out there and leave it to everyone to be a scientific jury. That may be convincing evidence to Zach, but not to Zach. Sorry about that. Okay, so it could, that was what Fisher wanted to do. And it drove people insane. They did not like it, to the point that they pressed Fisher to say, what is significant evidence to you? And in a footnote, be careful what you put in footnotes. He put in a footnote, for some, 10 out of 100 events may be convincing, 0.1. For others, 1 out of 100 would be convincing. But as for me, 5 out of 100. And now we all use 0.5. As if it came off Mount Sinai in stone. Okay? But there's nothing magical about that. All right? That has gotten ingrained. Fisher had opponents. They did not like each other. There was another group, Naaman and Pearson, Jersey, and Egon. They're very good with names and statistics. I told my wife we were ever having a son, I wanted to name him Egon. She said no. But we didn't have any sons. So set up a null alternative hypothesis. They said pick a type 1 error rate. Then, using a type 1 error rate, define the rejection region. In other words, draw the distribution. Put some areas, put some numbers in the tails, and if your statistic is so far out there, then you gotta reject. If it's not in the rejection region, you do not reject. You see these very different approaches. In the early 80s, when I was working on my undergraduate, I got all the way through a mathematics degree with 3 classes in statistics, and no one taught me a p-value. No one. I was taught to do every test using a rejection region. Works the same, you're going to come to the same conclusions, but these people, it was 2 very, very different philosophies. Notice, Fisher never gave you a type 1 error, an alternative hypothesis. Notice, they do not make any comment about a type 1 error rate, and Naaman Pearson said nothing about the p-value. No. Look, these people hated each other. Hated. 2 stories that I'm trying to make certain are out on time. 3 stories. Fisher had to start a separate journal because Pearson was the editor of the premier stats journal at the time and rejected anything that had Fisher's name on it without reading it. How's that maturity? Okay? Second, they hated each other so much, okay, that there was a conference, literally, Pearson's presenting a conference in France, giving his whole presentation on confidence intervals. This new concept, this brand new concept on confidence intervals. In walks Fisher, and this is recorded. In walks Fisher. And Pearson is just ready, he knows it's coming. Literally at the podium, people see him starting to sweat, just waiting for Fisher to attack him in public. He finishes his lecture, which was given in French. He sits down, Fisher walks out of the room. One of the people at the podium sitting behind puts his hand on Pearson's shoulder and says, "Calm down. Fisher doesn't speak French." But literally it's recorded that the guy's just like, massive sweat. Finally, the war gets so bad, Pearson decides he needs to relocate a little further away from Fisher, they're both at universities in England. So just to get away, just a little bit of difference, Pearson moves to California to start completely. How much they like each other. So, why don't you, and if you see any of this in our textbooks, where did the modern, now I'm going to answer just 1 minute, where did the null hypothesis come from? It's a bastardized version of the two approaches. We just went, bam, smushed it all together, glossed right over it, and it leads to a ton of confusion. Because how do I go from the p-value to power? You can't. You can't. It's two different camps. If you're going to go to power, you've got to stay on Neyman and Pearson's side. But the literature wants the p-values. So we're constantly trying to balance two different approaches to what's going on. Yes?
It's not really important. I was wondering if you knew why they hated each other so much.
Egos. I mean, there's only 3 things to manage in your academic career. And that's not teaching, and it's not service, and it's not research. The things you manage in academia are money, space, and income. It's true. I'm sorry, I was an administrator for a while. It's true. So one of the things you got to be very careful of is put your love of science before you put your love before anything else. These two people just got to where they had to be right. And it's kind of sad. Okay, it's a bastardized version of two very different. Does this mean it's useless? No, it's still very useful. But understand it's not the one tool. Not everything needs to be run through this blank. Okay? When you are building an experiment, you should ask, is it reasonable that I should be doing a hypothesis test? Not every experiment needs a hypothesis test. Okay? And please don't overinterpret significance. I'm not joking about this. Got way too many stories. A few years ago, I just finished a 5-year clinical trial. I met with the PIs. I designed the trial, helped them all the way through. I got there. I came in and I said, I've got the final results for the primary analysis. P-value is 0.052 because the journals were on 3 out of 3. PI broke into tears. And I'm looking at the person like, children okay? You okay? Bad day? Disagreement with the husband? What's up? She's distraught because 0.052 in her mind, that's not significant. And I look at her and go, trust me, I'm going to get this published. Trust me, the graph will convince anybody. Just because we're that little bit over doesn't mean all of a sudden there's no evidence whatsoever. Okay, so don't get so ingrained in there's a why. Okay? All right, so let's get the big things I want to make certain of. You understand why probability matters. I also wanted to show you that diagram. I wanted you to understand evidence beyond a reasonable doubt. Be careful for the major issues. You do not always have to set a type 1 error rate at 0.05. Though this seems to be convention, it should not be. Be careful. The null hypothesis does not have to be that a 0 or that 2 things are equal. Most important, please do not overinterpret a p-value. There are journals that are prohibiting the reporting of p-values because they believe they're completely misleading. It's not that they're misleading, it is that they are misinterpreted. Okay, so we're going to play true-false. A researcher reports that the p-value from his or her hypothesis is 0.01. Based on this information, the researcher has absolutely disproved the null hypothesis. True or false? False. Who all wants to go with false? A lot of people do this. How many want to say true? How many do not want to play my silly game? What's the problem? There's always a chance. Okay? You cannot say absolutely disprove. There's still, this data has a 1% chance of being observed if the null hypothesis is true. There's always potential for error. So you cannot say that. Okay, let's assume that we're using an alpha of 0.05 for all of these. Okay, based on, so here we go again. A researcher reports the p-value from his or her hypothesis is 0.01. The probability the null hypothesis is true is 0.01. True or false? You're not making me feel very confident here. And this is all about me. True or false?
I want to say false, but I...
You're right! Stop, go ahead. Go ahead. Well, you were going, but you want to say what?
But I can say why.
You can't say why. I'll tell you why. Okay? If you want the truth, go find the philosophy department. If you want evidence, you come talk to a statistician. I am never talking about truth. If you see truth, or if this is true or false, you have gone well beyond the limits of a p-value. Okay? Don't put that word anywhere near your conclusions. All right? I will say again, the correct interpretation, the p-value is 0.01. Then there is a 1% chance, there was a 1% chance of observing this data or data more extreme, assuming the null hypothesis is true. Under the condition that I worked the experiment, which is the null, and did the calculation, there's a 1% chance. It's rare, but there's a 1% chance that this could occur. But the p-value has nothing to do with truth. Okay? Or it cannot be allowed. And you know, my problem is I have researchers who will try to make that statement. I've worked with them for years and they will try to make that statement. Okay? This one, again, shoot it down. I'm telling you, it's false. You want a proof. You want truth, go to a philosophy department. You want a proof, find a math department. You want evidence, find the stats department. Okay? I don't do proofs. I do experiments. I draw conclusions. I make an inference. I live in a world where every experiment I could be making one of two mistakes. Okay? Just that easy. I cannot say I've proved anything. No matter, even if I have the $10 million randomized controlled clinical trial does not give me the ability to say I proved anything. Got on NPR about that the other day. Got on my soapbox. All right, this one gets a little bit harder. This is the psychology group. Psychology likes to do this. There's a 1% chance that he or she is making the wrong decision. Is that true or false? Psychology likes to report it this way. True or false? Is there a 1% chance that they're making a wrong decision? True or false? You should see the pattern now. What was the first three? What do you think this was? Yes. False. What's wrong? You're confusing p-value to type 1 error. You are interpreting the p-value as your error rate. What's the p-value? The p-value is the probability of observing the data, or data more extreme. I guarantee people they will not make an A in the class when they take it from it. If they stop their sentence there, they are guaranteed a B. It's the probability of observing the data or data more extreme given the null hypothesis is true. It's conditioned. I did the experiment under this belief. Okay? I compared it to this information. Right? How about this one? I thought it was easy. It's also false. Who said it? I heard somebody say it. Who said false? Why? You're exactly right. What did I do?
I don't know.
You made the first 4 false.
Huh?
You made the first 4 questions false.
Well, that's true too, but this is where people get into trouble. They reverse it. They're so desperate to say something about the null is true and to make a declaration about that. The p-values are always about the data. The hypotheses do not have probabilities associated with them. Think about where I started the lecture. Probability passes its characteristics into what? Data. Not into hypotheses, into data. So what has happened here is we've reversed it, and this is what has eaten literature alive. The probability that the null hypothesis is true given the data is 0.01. No, you've reversed it. Again, you tried to work in truth instead of anchoring on data. This is a Bayesian interpretation. There is a field of statistics that tries to do this. Actually, I think this is the field where we should be doing metabolomics. This is where we should be bringing Bayesians. I'm ready to hand all the genetic data to the Bayesians. Here you go, have fun. Because my methods do not work here. Okay? What about that one? What is it? Speak louder. It's true. It's true. Finally, we got to the one that is true. In your notes, what I want you to be able to do is go back and understand, look at those, when the notes come out, why those other ones are all false. Avoid them. Do not try to interpret your experiments that way. So, false, 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 Bayesian, false, true. Okay? Quick example, okay, so that we kind of ground it. I do an experiment, I'm looking at cholesterol levels. I have a very small experiment. I've got 10 women, 10 men, 12 women. I'm just wondering about, could there possibly be 2 probability distributions governing? Is there one probability distribution for women? Is there one probability distribution for men? You know, a lot of things vary by sex. And you know, this is probably one of the easiest ones for you to understand because we know height varies. We can observe it. Okay, does that mean every man's taller than one? No, my wife's taller actually. But we know that the distributions, if you graph them, they don't necessarily line up. That's what the hypothesis test, that's all the hypothesis test is trying to do. Is to say, so here's my data, we would summarize it, here's my sample size, here's my sample mean, here's my sample variance. I've got about a 5-point difference between the two, but, oh well, look at this. Oh, okay. All that first statement, mu1 equal to mu2, oh, be impressed with 3, la-di-da. The 2 distributions, mu represents the center of a probability distribution. I'm saying the 2 line up. right over the top of each other. That's all I'm saying. If they line up over the top of each other, all I'm saying is they're centered at the same place. That on average, women have the same cholesterol levels as men. To test that, I want to get some data. I want to calculate two sample means. See how close they are. If it's true, those two sample means could be relatively close to each other. If it's false, they could be far further apart from each other. When I see it, I ask myself, are they far enough for me to say they're different? I got a p-value of 0.0142. Somebody interpret that p-value for me. Interpret that p-value for me, and then I'll let you go. What does it mean? P-value is 0.0142. What does that mean? Okay. The probability that I would have been able to get this type of data, that I would have got these sample means and these variances, getting that type of data, given the two, there's one probability distribution. Given there's only one probability distribution, which is mu1 is equal to mu2, probability of getting that is about 1 out of 100. I'm going to say I get to the 5% level and I'm convinced, then I've got evidence beyond a reasonable doubt, and I reject and I decide there's two probability distributions. There's one distribution for men, and there's one distribution for women. That's the whole curve. That's all you can really say for all the elaborate statistics. That's all you get. Okay? And in conclusion, this is the way I would write it, to be very careful. There is sufficient evidence to reject the null hypothesis and conclude that the mean cholesterol levels differ between men and women. Okay? The probability of observing this data or data more extreme, assuming the null hypothesis to be true, is 1. That way I can give them very definitive. We have rejected. Here's the correct interpretation of the p-value. Always try to get that worked in. If you can do me one favor in your careers, just try to get the correct interpretation worked in. Don't assume that they know. All right, I have more slides, but I'm going to let y'all go. And I will see if we have an open week sometime. I'll come back and entertain.